this object, so they should stay where they are.
What? What? No!
But his first law of motion is pretty important. Now, it states that objects at rest will stay at rest, and objects in motion will stay in motion. So what exactly does that mean? Blowtorch, which I always get to use pretty much every day, and I'm going to try to heat the water up that's inside that sphere. Now, what happens when you heat water up? Most people would tell you, of course, it's going to boil. And when water boils, it produces steam. Now, in this particular case, the steam only has one way to get out, and it's the pipe on either side of our sphere. And we're also going to start to get some motion, which is that our little metal ball here is going to start to spin. And this is exactly what Isaac Newton was talking about. We had an object at rest, it just sat there, it didn't do anything, until an outside force, which in this case is the steam, starts it to spin. Now, according to Newton, this thing would continue to
learn about the concept of mass, difference between mass and weight, inertia, and Newton's first law of motion. What do you observe? Magically, this plate on top of the glass and balance this ball. What do you see? The ball doesn't move with the plate. It falls straight into the glass because of gravity.
I'm Bob Midden. For the next few minutes, we'll be discussing new demonstrations that can be performed using an air hockey table or a professional air table designed specifically for this purpose. The air cushion created by either device greatly reduces surface friction and provides an excellent means of illustrating Newton's principles. Small collapse. Repeat this action several times, noting the new direction taken by the puck each time it makes contact with the striker. Ask your students to explain why the puck is changing direction. Be sure they understand that even after the change in direction, the puck travels in a straight line.
What do you predict will happen? Did you get it right? This time, Dr. Smith has 3 solid steel balls, a small one, a medium-sized one, and a large one, placed at the top of the ramp. What do you predict will happen?
You might have at home a little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee and we'll pull it back. And let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. And there you have it, Newton's second law of motion in action.
To Aristotle, this ball swinging around a string is in uniform circular motion. You can see it's moving at a constant speed around a simple circular path, keeping it swinging around. As soon as I let that force off, it just basically falls back down and stops my head. As I move it around, if I want it to go faster, I have to put in more force, but when I regularize that force, it swings around at a constant speed, but the direction is continually changing due to that acceleration.
of the cylinder on the gas. And then that gas pushes back on the cylinder and on me, accelerating me. So
4, 3, 2, 1.
And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball, I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me.